I think it's safe to start now. So again, a warm welcome from my side. My name is Rolf Lawrence and I'm from Flownex. I'll be presenting this webinar regarding molten salt reactor modeling. And to quickly give you an overview of what we will be discussing in this section, first of all, I'll talk a little bit about Flownex in the current nuclear industry. Then we'll go to molten salt reactor modeling capability. So what makes Flownex unique, or what makes Flownex capable of being a molten salt reactor modeling tool? We'll also talk about Flownex, the model itself, a molten salt reactor model that I'll be showing you guys. And then in the end, we'll have some questions, or there will be time for 2 or 3 questions. Now, just because the questions will be at the end, that doesn't mean that you are not allowed to ask any questions in between. So feel free to unmute yourself and ask a question. If I may be going too fast or something is not clear, you're welcome to ask questions in between as well. Okay, so Flownex in the current nuclear industry. Obviously, for us, I think, and for myself, there are 2 main words that has been flying around for quite a while. It's the Generation 4 initiative, and then also the Small Modular Reactors, SMRs. So those 2 words are the 2 words that we are trying to align ourselves with in the nuclear industry from Flownex side. So as far as we can, we try to hear what are the client's requirements, what do they need from a software, and then we try to adjust to that within our capability. Flownex first developed pebble bed reactor modeling capability. A few years back, South Africa started with the PBMR project. That was a pebble bed reactor, and Flownex got involved with that, and most of the development regarding our nuclear capability was during that time, and we also got our nuclear accreditation during that. We then move on from the pebble bed technology to incorporate block fuel type reactors, plate fuel, and then also cylindrical fuel rods. So from the pebbles, we moved on, we expanded that to be able to take all these other kinds of fuel types into account. And then the last one that we did, that we are very excited about, and obviously that is what this webinar is all about, is the molten salt reactor capability. Okay, so to go into a little bit more detail on the molten salt reactor modeling, what makes Flownex capable? I'd say it's the fact that we have custom plant components. So those of you who have worked with Flownex previously or have seen it previously will know that we have a library of components such as heat exchangers, pumps, valves, pipes, all of those. And for those of you who haven't seen Flownex previously, I'll give a quick introduction as soon as we go to Flownex itself. But we have plant components that has been customized for the power industry, whether it's a Rankine cycle that's driven by fossil fuel or whether it's a nuclear plant. So that will be the first thing. The second thing is we've set up our reactor model to include your specific geometry specification and then also neutronic specification. So for each type of reactor with various geometries, with various neutronic specifications, Flownex can accommodate that. On that note, I must just say again that remember Flownex is a systems modeling tool. So it's not a 3D CFD tool, it's a systems modeling tool. It looks at the system as a whole, and the reactor will also incorporate everything that is important in terms of systems modeling. So this geometry and neutronic specification is into the level where we feel you can successfully simulate the whole system with your reactor, with your heat exchangers, with your steam generator, with your turbines, with your pumps, all of that on a detail level that will show you how your system will behave. Thirdly, fluid specification. So in terms of molten salts, there are a huge number of molten salts that are targeted to be used in these applications. And all of those fluids, although they may not already be included in Flownex, because there's a huge library of fluids already included in Flownex, if there's a molten salt that's not included, you can by yourself just go and create that fluid within Flownex with its applicable density, viscosity, the specific heat values. All of that can be manually created, and then that specific molten salt will be modeled accurately within Flownex. And then fourthly, as most of you might know, Flownex can solve both steady state and then also transient conditions. And that transient modeling can be incorporated with the control and instrumentation library that we also have in Flownex. So you can have a live simulation, a real world simulation almost, of your plant. Again, Flownex is used to see what will happen on system level, for example, with a pump trip, with a loss of coolant accident, with your control rods being fully inserted, natural circulation that will take place during no flow conditions and all of that. So that is what we are excited about with Flownex, and where we feel that we can add a lot to the market out there. In terms of molten salt reactor modeling, or actually in terms of reactor modeling in general, I'm quickly going to give an overview of how the model interacts with the practical plant. So here you can see a reactor. The fluid will come in on the outside of the reactor core. This might be to cool down the reactor pressure vessel, and then it will go into the core, flowing down, going to my steam generator, changing heat, and then going back again, flowing up through my cooling passage, and then into the core. So this is just an example to explain to you how we go from here into a model that we'll be able to simulate in Flownex. In Flownex, we have an axisymmetric approach. That means that this block here that I've drawn, just get to that quickly again. So this block here will be what we model in Flownex, and then that will be revolved 360 degrees in order to form an axis symmetric reactor. So in our approach, it's important to remember that it's been set up in this way. So we'll just be building a reactor, half of it in one plane, and then that plane will be revolved 360 degrees. Okay. It will look something like this. So what we have here is the cooling flow coming from the outside, then flowing through the passage. So there are various passages that it will flow through the outside. Then it will come into the core. So this yellow part is the core, and it will flow out again to go to my steam generator. So in Flownex, the first step will be to set up this geometry chart. We call this the geometry chart, and we build this with these blocks. So you can see there's various columns and various rows, and each of these I can name them according to this region. Let's say a pebble bed. There's also a general field zone that I'll introduce you just now, and then single cavities. So all these regions, I can use them as building blocks in order to create my geometry. Remember again, it will be half the geometry in one plane that will be revolved 360 degrees. Once I've set this up, Flownex will, in the background, create a flow network with heat transfer and then also the flow components. And it will look something like this. Now, let's see, there it comes. Okay. Now, I'm not going to go into the detail involved with this discretization of this flow and heat transfer network, but basically it will be the flow coming from the outside, going into the reactor, and in here I will have my pipes or my flow components. There will be nodes, there will be heat transfer within the field itself, So you can see there will be conduction, convection, and then also radiation taking place in this model. So all of this is accounted for in the background once you've set up your geometry chart. Then from your geometry chart, you'll also specify a neutronics map or a neutronics chart that will then enable the Flownex model to calculate the fission physics heat map. The neutronics in the heat map will then be passed over to the Flownex temperature map, or then the heat exchange that's taking place, which will then be passed back again to the neutronic side. So depending on my temperatures, there will be a certain neutronic response, and then that will be fed back into my temperature solver, and that will then go back into my neutronic calculations up until I have a conversed solution for that time step. All right, so in terms of the default, in point kinetics, we have feedback coefficients, we have the heat input map, we have temperature feedback to that, we have the control rod reactivity that influences my point kinetic model, and then also the neutron precursors. We also have a scripted neutronic model. I'll go into that a little bit later, but there will be user editable neutronics models and then also the user definable feedback mechanisms. But I'll get to that a little bit later. So just to quickly recap on this, when I go into Flownex, when I build my reactor, I first set up a geometry chart which specifies where I have solid sections and where I have my field sections and where I have flow sections. Then on that, I add my neutronic chart, which will then interact with the thermohydraulic solution in order to iteratively calculate what happens with my fission products and with my neutronic side, and then also how that influences the temperature and vice versa. Okay, so this is just a quick overview. I'm not going to go into too much detail on this. There is still a lot of exciting stuff that I want to talk about in the next 15 minutes. Okay, so let's go to Flownex. All right, so those of you who have seen Flownex previously, this is the interface that we are working with. Here in the middle is what we call the canvas, and this is where we build our networks. We have a bunch of Flownex components, a whole library of Flownex components, like, let's look at these on the electronic side. These are the pipes. We also have turbos and pumps. And in order to build my network, I can simply drag and drop these components onto my canvas. So let's start off with the nuclear reactor component, drop it there. Then I can connect a pipe to that. So it will automatically connect to my reactor. And I can also, let's say, take one to the inlet. And I can then also add my pump to that. So this will be some kind of a molten salt flow driver. Then obviously I need to add boundary values since I'm only modeling a section of the whole network. So I can go to boundary values, one on the inlet, one on the outlet of my network, and here I can specify the inlet conditions and the outlet conditions. So all of these components has their own set of inputs required in order to model them, and then also all the flow results that you might be interested in: pressures, temperatures, mass flows, volume flows, densities, specific volumes, viscosities. So all the flow and heat transfer components that you might be interested in as a user. In terms of the reactor, we will need to specify the power of the reactor, the control rod depth, and then also add the reactor chart editor. So this will be the geometry chart, and then later also the neutronic chart. In terms of results, For the reactor itself, this is now from for the reactor as a whole. I can have average field and moderator temperatures, the total power, decay heat, fission power, then also my control rod results and my reactivity results in terms of my xenon, my iodine, my control rods, my total reactivities. So all of these are displayed for my reactor as an integrated component. Okay. We also have the reactor's detailed results, and I will show that to you a little bit later. So this was just a quick illustration of how we will set up a Flownex network. In terms of the reactor itself, I need to generate a reactor geometry chart. And for that, I will go to charts and lookup tables, go to my nucleus section, and in my nucleus section on the reactor geometry charts, I can create a group and let's say add new. Edit this one, and this is the interface that I will see. So I'm going to go very quickly over a few principles in building a reactor chart. So first of all, we take the number of X zones, that's the radial direction, and the number of Y zones, that's the axial direction. So let's say there are 3 zones radially and 7 zones axially. So this will then be created here. This is my map then, and I can create flow elements here. Let's say on this block, I want to add my field zone. So I can double click on it or press edit, go to general field, and then my inputs required for that model will be adjusted here. In terms of power distribution, I can add a power profile, and in terms of the field geometry and increments, I need to specify for the molten salt region what would be the volume fraction per zone volume, per zone solid volume, and all of these inputs. What is important for the molten salt reactor modeling at this stage is that we want to generate the heat in the fluid itself. So we need to activate that tick box. So the heat is generated within the molten salt itself. We also want to use the fluid temperature in the field for neutronic feedback, and the same with the moderator as well. So it's important for molten salt reactors to select these 3 tick boxes in order to communicate to Flownex that the heat is generated in the fluid and not as in the case with, say for instance, a pebble bed where the heat is generated in the pebbles. So it is important to mark those 3 tick boxes. Again, as I said, I'm running extremely quickly over this. Please try to bear with me. This is not the focus of this webinar. The idea of this is just to give you a feel or an overview of the capability of Flownex towards molten salt reactors. Okay, so in this way, I can then set up my geometry chart, and with the neutronic options in my field zone, I need to add a neutronic chart. So here, automatically, it's already adopted the HDR10 molten salt neutronic chart, and I'll quickly show you where this comes from. So let's cancel. Under solid field neutronics charts, or actually just neutronic charts, there is the HDR10 molten salt. If I edit that, then I can see here is my chart with which I can set up my neutronics. So this chart is based on a 6-group points kinetic model, and there I can add all my neutronic precursor constant values, my decay heat parameters, my reactivity feedback coefficients, and then my control rod influence on reactivity. So important to understand, I will start off with my geometry chart. Then I will specify a neutronic chart. I will link these two, and then that will be assigned within my reactor here to say, let's say I want my MSR, and this is the one that we've just used. So in this way, it will take up the geometry that I specified here and also the neutronics. Okay, let's go to a live model or a working model, and I'll show you how this works. So in this network here, I've set up, it's basically the same. This is a 10 megawatt reactor. I have as a geometry my molten salt field zone. So let me show you how this works. The molten salt field zone, that's just, it has an inlet here, and then my field zone. So this is where the molten salt will obviously exchange heat or build up heat due to the neutronic actions, and then again exit there. This will just be a side reflector that I'm modeling here as a solid. So you can see that's the side reflector. Okay, and this is just a very simple model for illustrative purposes during this webinar. I can now press solve. Flownex will then calculate everything. This is now for a steady state. So I will be able to see that I came in, my boundary value said my temperature is 550 degrees on the inlet, and on the outlet it comes out at 577. So with a mass flow of 150 kilograms per second, this 10 megawatts of heat accounts for the temperature increase up to 577 degrees C. Now I can go to the internal results or the detailed results of this reactor by going to my results tab here in Flownex and then go to this note file. I can click on that, and here I will get my incremented results for my reactor. So let's say for flow node temperature results, this will be each increment as I go on radially outside. So 0 will be the center. On this one with the rows, 0 will be the top of the reactor, and this is my temperatures as I go down. So it will come in here, there's my 550. It will heat up through my reactor and then go out at 577. Now it is important to note, if you look at these results, I just want to mention this. There are mainly two types of molten salt reactors. The one is where you have solid structures within the reactor itself, like your moderator, carbon moderator or whatever. So there is a fixed flow path for your molten salt to go from, let's say, for instance, from the bottom to the top. So just visualize that. I have some solid structures within my reactor, so there's a fixed flow path from the bottom to the top. That's the one type of reactor. Another type of reactor is a pool type. So my moderator will be included, or the moderating effect will be included within the molten salt. That molten salt will just come into my reactor region. It will mix, it will flow in two-dimensional flow paths, actually in three-dimensional flow paths, mixing and then go out again. So this example that we have here is the one where I have structures, so a fixed flow path from the bottom to the top, and therefore you will see that this result will make sense in terms of that. So the flow will go radially in, and then you can see these as different channels. These are all the results. I have velocity results, I have the amount of heat generated results, I have my mass flows, I have my densities. So these are all the results, all the detailed results of my reactor. In order to visualize them, I can take these results and copy them to Excel. So as an example, I'll quickly show you that. Take these values, copy, go to Excel. I've already set this up and paste it. Just want to go to data, text to columns, space. All right. So there I can see my temperature profile through my reactor in Excel. And I can go to my 3D rotation, and then I can rotate that in order to get an idea of what goes on in my reactor. So this will be the temperature results. Let's say, for instance, I want to see the heat generated in my reactor. So I can go to generated heat results. Again, take those values, copy them, go to Excel, paste them, and here you will see I have an actual profile. So I'll go back to the Flownex model just now, and then I can visualize that to see a quadratic actual profile within my reactor. To go back to Flownex, on my geometry chart, in my power distribution, this is where I specified that curve. So this is that actual power curve profile. I specified it here. Okay, so this has been a mouthful, but just to show you guys, this is how you will set it up and where you'll get the results. One more thing that I want to show you is the script quickly. So just disable this one, enable this page. What is extremely powerful with this script is that the chart is only limited to a 6-group point kinetic model. With the script, I can have as many point kinetic groups as I'd like. I can add the heat wherever I like in the reactor. So this script gives me complete freedom in terms of characterizing the neutronic part of my reactor. So I still use the same geometry chart. So it will still be this geometry chart, but here in this case, I will say for my neutronics calculation, use the script component. In my script component, you'll see there's a lot of coding involved, but once you've got accustomed to the coding inside here, it's very easy to use it in order to customize your neutronic setup. So here I will go to my neutronic precursor groups, and I can change my constants, and I can add more groups or take away some of the groups. So the power of the script is that it allows complete freedom in terms of characterization. I quickly want to show you a transient simulation, so a dynamic simulation, and the influence that my control rods have on that. So the bar I'm having here on my left-hand side will be my control rods. And if I take this bar down, it means that my control rods is inserted fully. And if I move it up, then it's extracting my control rods. So let's start off at 0. Let's go to my inputs, control rod depth. I want it in the middle. And then I can start my transient conditions. So here on the graph, you'll see the green line is my control rod depth. My blue line is my reactor power, and my red is the temperature. So currently, although it seems as if there's a lot going on, it's actually just decimal changing. If I now take out my control rod somewhat, you'll see, so I have a jump in my control rod position, and then immediately I have response in terms of my power profile or my power value, and then also my temperature. And then if I want to fully insert my control rods as imagine some emergency condition, you'll be able to see in real time, or actually faster than in real time, what will happen with my power profile due to my decay heat, and then also my temperature as that goes on over time. Lastly, just stop this. I want to show you another Flownex network where this has been integrated with the rest of my network. So here you can see this would be my primary network with the reactor here on my left-hand side. That will then go over with a heat exchanger to my secondary molten salt, which will then again exchange heat with my steam side here. So here I have steam, I have my secondary molten salt, and then my primary molten salt here in the reactor section. And in this way, I can even add my turbines and my Rankine cycle, my steam cycles, feed water heaters, condensers, and pumps up until I have my complete network with control and instrumentation, and then I can do some real examination of my system. So that then concludes the Flownex simulation part of it and the Flownex model. And then lastly, I want to give time for some questions. So any questions, you can either unmute yourself to ask a question, or you can type in a question, and then I'll try my best to answer that.